educational satellite television programs.
Hello, teacher. Hello, students. Welcome to today's lesson on the principle and application of mathematical induction. In the last lesson, we learned the definition of mathematical induction and how we could apply it to mathematical proofs. Today, we are going to study this idea further. We will also learn to discern when proof through mathematical induction is appropriate. Are you ready, students? Let us begin with a brief quiz. Please consult your notes from the last lesson and define the principle of mathematical induction. Take a moment to do this now, students.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. Check your answer against my definition and make sure that they are identical. The principle of mathematical induction is as follows. For a given assertion involving a natural number n, if the assertion is true for n is equal to 1, it is true for n equals k plus 1 whenever it is true for n equals k when k is greater than or equal to 1, then the assertion is true for every natural number n. As we learned last lesson, this principle can be used to prove assertions that cannot be proved through calculation. Let us look at another example. Let us make the assertion that n cubed minus n is divisible by 3. First, we can test the validity of the statement by assigning a value to n. For this example, let us assign n a value of 5. 5 times 5 times 5 equals 125. Subtract 5 and the difference is 120. 120 divided by 3 is 40. Like last time, our assertion seems to hold. But we cannot possibly assign every possible value to n and calculate the result. There are infinite possible values, so the process would take an infinite amount of time. It would also be extremely boring. Yet, unless we know for certain that our assertion applies to every possible value of n, we cannot consider it proved. Therefore, this is an appropriate case in which to apply the principle of mathematical induction. The assertion is true when n equals 1 because 1 cubed minus 1 is 0. 0 is divisible by 3. For n equals k being greater than or equal to 1, we may assume that k cubed minus k being divisible by 3 is true for a natural number k. We must show that this is also true for n equals k plus 1. Therefore, we must demonstrate that k plus 1 cubed minus k plus 1 is divisible by 3. Do you remember this technique, students? Take a few moments and try for yourselves. You may get started now.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Hello there. I hope you did well. Get ready to follow along with the proof, everyone. Let us expand the statement k plus 1 cubed minus k plus 1. It can be expressed as follows. K plus 1 times k plus 1 squared minus k plus 1. Then we expand k plus 1 squared, giving us k plus 1 times the sum of k squared plus 2k plus 1 minus k plus 1. We then expand everything, giving us k cubed plus 2k squared plus k squared plus 2k plus 1 minus k minus 1. With grouping and simplifying, we get k cubed plus 3k squared plus 3k minus k plus 1 minus 1. We then get k cubed minus k plus 3k squared plus 3k. This may be expressed as the difference of k cubed minus k plus the product of 3 times k squared plus k. That is all we need to make our proof, students. Since we assumed that k cubed minus k is a multiple of 3, k cubed minus k equals 3p, where p is part of the set of natural numbers. We may substitute the term 3p plus into our equation, giving us the equation 3p plus 3 times the sum of k squared plus k. We can factor and write this as 3 times the sum of p plus k squared plus k. Therefore, k plus 1 the whole squared minus, in brackets, k plus 1 is also a multiple of 3. We have made our proof. We can safely conclude that by the principle of mathematical induction, n cubed minus n is divisible by 3 for any natural number. It is time to demonstrate what you have learned, students. Please select a partner to work with. Here is an assertion. 6 to the power of n minus 1 is a multiple of 5 for all values of n that are natural numbers. Use the principle of mathematical induction to prove the validity of this assertion. Please do your best, and I will see you in a few minutes.
Students, Let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. I trust that you and your partner were successful in making the proof. Let us begin with verifying the assertion by giving n a value of 1. 6 to the power of 1 minus 1 is 5. This is clearly divisible by 5. So, the assertion is holding so far. Assume that n equals k, where 6 to the power of k minus 1 equals 5m, m being a natural number. Then 6 to the power of k plus 1 minus 1 equals 6 times 6 to the power of k minus 1. We then add 6 and subtract 6. We rearrange the equation. We factor 6 out of 6 times 6 to the power of k minus 6, giving us 6 times 6 to the power of k minus 1 minus 1 plus 6. We simplify to get 6 times 6 to the power of k minus 1 plus 5. Since we assumed that 6 to the power of k minus 1 equals 5m, we get 6 times 5m plus 5. We then factor out the 5 to get 5 times 6m plus 1, which is divisible by 5. Therefore, for each natural number value of n, 6 to the power of n minus 1 is a multiple of 5. You have proved the assertion, students. Congratulations! That is the end of this unit, everyone. We have learned about logic, the different types of proofs, and the principle of mathematical induction. I will see you in the next unit. Until then, thank you, teacher. Thank you, students.